All right, I want to do some more examples of the chain rule, and I believe last Monday your homework was through 65. I've answered the few emails that I got with questions on those, so I want to pick up approximately, well, 66, I suppose, and work as many examples as I can in about 45 minutes, and hopefully that will give you some more examples to go by on finishing up the 3.4 homework. This is page 162, and I do want to start with number 66 because there's something that I need to show you there. If I leave that as it was originally given to me, then I don't just have cosine x, I have cosine ugly. And not only that, I have cosine ugly to a power. So I'm always going to ask myself, is there a simpler way that I could rewrite this to avoid using the power rule or quotient rule, product rule, anything that I can? It would be very easy to say 2x times 2x is 4x squared. And that would avoid me having to say that this was ugly to a power. Now it's just cosine ugly. I can take the derivative term by term. The derivative of the first term is 3. The derivative of -5 times a function, just keep up with the -5 and differentiate the function. This is cosine ugly. The derivative of cosine ugly is negative sine, same old ugly, times the derivative of the ugly, which would be 8x. Here, that's my ugly. Here, this is derivative of the ugly. And then just clean that up as much as possible. You have a negative times a negative is a positive, and then a 5 times 8x is 40x, and not much you can do with the sine of 4x squared. So it's absolutely fine to leave your answer like this. When I glanced over to see how it was written in the solutions manual, I saw that they had converted it back to sine of 2x in parentheses squared because that's how the original problem was written, but that absolutely doesn't make any difference. Either this or this would be perfectly fine for the answer. All right, I need to show you something about 68. What I want to show you here is what a difference the parentheses make. Here it's the x that's being raised to the 1/3 power. Here it's the sine that's being raised to the 1/3 power. So in this first term, I'm looking at that as being sine of ugly, and the derivative of sine of ugly is cosine, same old ugly, times the derivative of the ugly. Now, when I write the derivative of the ugly, I need brackets or braces or something that will keep me from multiplying this cosine x to the 1/3 by the derivative of the x to the 1/3. I'm going to use parentheses around the cosine and say that's 1/3 x to the, subtract 1 from the exponent, 1/3 x to the -2/3. Derivative of sine ugly is cosine ugly times the derivative of the ugly. But here, I have to look at the ugly, or let me just call it v since I've already used u for something. This is the derivative of the ugly. This is v to the 1/3. The derivative of v to the 1/3, bring the exponent out front, 1/3 sine x to the negative 2/3, because I'm just treating that as an ugly. Derivative of v to the 1/3 is 1/3 v to the negative 2/3 times the derivative of whatever v was. The derivative of sine x is cosine x. That's the derivative of v. And then look to see how you can clean that up. There's really not very much you can do because none of your trig functions have the same argument. You could write this first term as cosine x to the 1/3 over 3x to the 2/3. And you could write the second term as cosine x over 3 sine x to the 2/3, or that may be written without parentheses as sine to the 2/3 of x, because these two ways of writing a trig exponent or trig function to an exponent are equivalent. It's the sine that's being raised to the 2/3 power, not just the x, as is in the case there. And I wouldn't expect you to get a common denominator and add those. I mean, that's good enough. You can leave your answer like that. The only thing different that they did in the book, and it absolutely doesn't matter, they factored out a 1/3 and had everything else left in brackets. Let me see if my microphone is still working. I think so, and I hope so. I'm going to keep talking. All right. Number 72. Y equals e to the negative x squared. That's not just e to the x, it's e to the ugly. And the derivative of e to the ugly is e to the same old ugly times the derivative of the ugly. Derivative of negative x squared is negative 2x. And there's really no way to clean that up other than just write the negative 2x in front of the e to the negative x squared. Number 74, same thing, but it's going to use the product rule. Make sure that when you say the first times the derivative of the second, the derivative of e to the negative x is not only e to the same old negative x, but you also have to take the derivative of the negative x. So first derivative of the second would be x squared e to the negative x times the derivative of negative x is negative 1. And then you'd still have the second factor times the derivative of the first. Let's see. What about the only hint that I'm going to give you about 76 is there's a way you could write that exponent and not have to use the quotient rule. I would write that exponent as e to the negative 3t to the negative 2. The derivative would be e to the same old ugly, and then the derivative of the negative 3t to the negative 2. Let me leave that one and talk about 78. Another thing that it really takes practice to train your brain to look for is when you're asking yourself, is there a way that I could write this so that I didn't have to use the quotient rule? If you'll think about, go back to your properties of logarithms, you know that a log of a quotient can be written as the difference of two logs. So without using any calculus at all, you can rewrite that problem so that you don't have to use the quotient rule. The log of a quotient can be written as the difference of two logs. Now make sure you don't distribute log through a sum. The natural log of 1 plus e to the x is not natural log of 1 plus natural log of e to the x. This is not multiplication. You can't distribute it. All right. This is, let's call that ugly, and that my v. The derivative of natural log of ugly is 1 over the same old ugly times the derivative of the ugly, and the derivative of this ugly is e to the x. Of course, you could put that as e to the x over 1. Then the second term, the derivative of natural log of v, is 1 over same old natural log of v times the derivative of the v. The derivative of negative e to the x is negative e to the x. So when you clean that up a little bit, notice that you have a negative here times a negative here. That gives you e to the x over 1 plus e to the x plus e to the x times 1 minus e to the x. And I would suspect that in the solutions manual, they would go with write your answer as a single fraction, factor it as completely as possible. If you multiplied this first term by 1 minus e to the x over 1 minus e to the x, you would have the common denominator, which notice this is something times its conjugate. When you FOIL it, the outer and the inner terms are going to cancel, and that's going to leave you 1 minus e to the, add the exponents, and you get e to the 2x. And then you would have to multiply your second term by e to the x, multiply the second term by 1 plus e to the x over itself. And that would be over the LCD. Then you could either think of this as, you could either distribute the e to the x, or you could factor out the e to the x. The easiest way for me to think about it is factoring out the e to the x in the numerator. And what that will leave in the numerator is the 1 minus e to the x plus the 1 plus e to the x. Look how neatly that simplifies. This negative e to the x plus e to the x is 0. This 1 plus 1 is 2. 2 e to the x over 1 minus e to the 2x. It was the algebra, the cleaning up, that was a little bit ugly there, not the calculus, actually. The calculus was pretty easy. All right. That was 78. 80, very similar, using the quotient rule. Actually, You wouldn't have to use the quotient rule on number 80. Let me show you why. If you did use the quotient rule when you got to the second term of the numerator, which would be the numerator derivative of the derivative of that denominator is just 0. So that would kill off your second term of the quotient rule. Why not just write this as 1/2 e to the x minus e to the negative x and take that derivative term by term? This is a constant times a function. So the derivative, just keep up with the constant and differentiate this function term by term. The derivative of e to the x is e to the x. The derivative of e to the negative x is e to the same old negative x, but then also the derivative of that exponent. Use of parentheses is important there. That -1 is only multiplied by this negative e to the negative x. That answer will probably be written as e to the x plus, because of this negative times negative, e to the negative x all back over 2. All right. Look at 84. It's tempting to say that you would need to use the product rule there because you have e to the something times natural log of x. But this e to the something is just a constant. E is about 3. 3 cubes about 27. I suspect this is somewhere around 25. So this is just a constant times a function and doesn't require the product rule at all. That derivative would be just keep up with the constant and differentiate the function. That answer would probably be written as e cubed divided by x. '86 is tricky. Well, I don't like to call it tricky. I'd like to call it just think about what it is that you're facing right there. Y equals natural log of e to the x. What is natural log of e to the x? Natural log of e to the x is just x, because natural log and e undo each other. So the derivative of that function is just the derivative of x, which is just 1. And that's all there is to it. Let's see. Let's look at number 92. There's actually a couple things that I could do to make this a little bit easier to differentiate. If I look at it as being natural log of ugly, then within the ugly, I have another little ugly to the 1/2 power. That would take the power rule and the chain rule. If instead I wrote this as natural log of x squared minus 9 to the 1/2, then you should remember from college algebra that it's quite legal to bring this 1/2 out front, and then you just have natural log of plain old ugly, not ugly to a power. So I would write that as 1/2 natural log of x squared minus 9, where only the x squared minus 9 is my ugly. Now I have the derivative of a constant times a function. Keep up with the constant. Take the derivative of the function. The derivative of natural log of ugly is 1 over same old ugly times the derivative of the ugly. Then your 2's cancel, and that just simplifies to x over x squared minus 9. I'm looking for something just a little bit uglier, and then we'll go to a problem that says find the second derivative. Number 104 is about the ugliest thing I can imagine. Let me say one thing about number 98, and then I'll go to 104. 98, similar to what we did on 92, where we wrote that as x squared minus 9 to the 1/2 and then brought the 1/2 out front. I could do the same thing on 98, write that as natural log of ugly to the 1/3, and then bring the 1/3 out front. Actually, I don't want to do the calculus here, but let me show you what that would look like just when you rewrote the problem to make it easier to differentiate. You have to be very careful with parentheses. You bring the 1/3 out front, but in that same step, to avoid having to use the quotient rule here, you could say the log of a quotient can be written as the difference of 2 logs. But you have to have those 2 logs in brackets because 1/3 was the exponent of both the numerator and denominator. So 1/3 is the coefficient of both of those. Now you can take the derivative term by term, keep up with the 1/3. Derivative of natural log of x minus 2 is 1 over x minus 2 times the derivative of the x minus 2, which is just 1, and the derivative of natural log of x plus 2 is 1 over x plus 2 times the derivative of the x plus 2, which is just 1. And then I'm sure that that's not the answer in the back of the book. They will have gotten the common denominator and simplified that to a single fraction, but I want to go on to something a little bit uglier. Well, actually a lot uglier. Number 104. That's about the most horrific function that I can imagine, the natural log of secant x plus tangent x. Really not all that difficult to differentiate, though, if I call this my ugly then that's just natural log of ugly. By the way, those absolute values here don't affect the derivative. They just allow you to use a wider range of x's. You can't take the natural log of a negative number, but by finding secant x plus tangent x and then taking the absolute value, you can use all the values of x for which secant and tangent are defined. Because when you take the absolute value of secant x plus tangent x, you'll get a positive number, and you can take the natural log of a positive number. You don't have to worry about the absolute values affecting the derivative, though. The derivative of natural log of ugly is 1 over same old ugly times the derivative of the ugly. The derivative of secant is secant tangent, and the derivative of tangent is secant squared. So here's 1 over ugly, here's the derivative of the ugly, and notice I could factor a secant out of that numerator. If I factor a secant out of that numerator, what will I have left? All that's left of the first term is tangent x, and all that's left of the second term is another secant x. And then guess what? That whole derivative cleans up to be just secant x. All right. I just realized, I very much anticipate that one of the questions you may have asked me from the homework, if we had gotten to be in class Monday, was number 41. Because the algebra on it was rather ugly, I want to do it before I go on to second derivative problems. So backtracking just a little bit, let's look at number 41. G of t equals 3t squared over t squared plus 2t minus 1 to the 1/2. That denominator in the book is under the radical. I'm going to go ahead and change it to t squared plus 2t minus 1 to the 1/2. And that's not the derivative, that's the original function. So the derivative, remember I never rewrite the a quotient as a product, in my opinion, 99 times out of 100, but not 100 out of 100. It doesn't make the problem any easier. So I'm going to go ahead and use the quotient rule here. I'm going to start with the denominator. Times the derivative of the numerator is 6t. Then minus the numerator times the derivative of the denominator. And I'm looking at this denominator as being ugly to the 1/2. The derivative of ugly to the 1/2 is 1/2 same old ugly to the negative 1/2. But then don't forget the derivative of the ugly. If this is the ugly, t squared plus 2t minus 1, then its derivative is 2t plus 2. And all of that is divided by the denominator squared. That's about as ugly as any of the problems we cleaned up the first day of pre-calculus. This is what it was all leading toward. Let's see. I don't know if you would happen to think of this or not. Number one, take a deep breath and say to yourself, this numerator, no matter how ugly it is just a binomial, where this is the first term and all of that is the second term. Now, what I just noticed that I said, you may notice, you may not, I could factor out a 1/2, or within this second term, I could factor a 2 out of the 2t plus 2, multiply it times the 1/2, and at least not have fractional coefficients anymore. What I'm saying is, this first term, I'm not going to do anything in this step. But the second term, all I'm going to do is factor a 2 out of this last factor and multiply it by the 1/2 to get rid of the fractions in that term. I'll still have the ugly to the negative 1/2, and after I factored a 2 out of that term, I'd have t plus 1. In the denominator, I can say ugly to the 1/2 squared, raise a power to a power, you multiply those exponents, you just have ugly. All right, let's see what we can factor out of the numerator. I could factor out a 3 and a t, and t squared plus 2t minus 1 to the lowest exponent. So in the numerator, I'm going to factor out a 3t times t squared plus 2t minus 1 to the negative 1/2, and then in brackets beside that, I need to write what's left of each term of the numerator. The first term, if I factor a 3t out of a 6t, I'm just left with a 2. And if I factor this to the negative 1/2 out of this to the positive 1/2, just subtract the exponents. 1/2 minus negative 1/2 is 1/2 plus 1/2, which is 1. I don't have to write it, but I wanted you to know that I did figure out that that exponent was 1. From the second term, if I factor out a 3 and a t and this ugly to the negative 1/2, all I'll have left is the other t and the t plus 1. Pretty easy after that. I'm going to clean up what's inside brackets, and I'm going to bring this ugly to the negative 1/2 to the denominator. In the very last step, I'll end up adding those exponents together. But in the numerator, there's my 3t. I brought that down because of its negative exponent, but I had to factor it out first. Now cleaning up what's inside brackets, I would have 2t squared plus 4t minus 2 minus t squared minus t. I distributed that negative t on the end. And finally, When I combine like terms in parentheses, that would give me 2t squared minus 1t squared is t squared. 4t minus 1t is 3t, and minus 2. Like I said, in the denominator, since these two expressions have the same base, I just need to add the exponents and get that to the 3/2.